Yeah, I can start. So I'm going to tell you something about my final project, in which I aim at optimizing the planning strategy within the judiciary. So the problem I've got was the timeliness of the judiciary systems is too late. So this means that the work is not being processed within the formulating norms, which causes people are waiting for their verdicts. And my approach is to make an optimal allocation of judges and legal assistants. And in my project, I focus on commercial law. And commercial law has certain norms. So which I already said that the problem is that the work is not being processed within the formulated norms. So you have an arriving case, and the norm for commercial law is that the hearing has to take place within a maximum of 12 weeks. And when the hearing has taken place, the verdict has to be written within a maximum of 6 weeks. So for the approach, I use mathematical modeling. And in my model, I want to plan 3 appointments per case. So I have a preparation of a hearing, I have the hearing itself, and I have the writing of the verdict. And this approach is inspired by the stochastic resource constraint project scheduling problem and the multi-appointment scheduling problem in healthcare. And these are problem formulations in literature, and those are used to solve planning problems in revalidation and radiotherapy, in which multiple appointments have to be planned for a certain patient. And I used the mathematical approach, starting with the mixed interlinear program, and I expanded to Markov decision program. So I started with the mixed interlinear program. In the mixed interlinear program, all appointments are known in advance. And you have to schedule those appointments. You have to make a decision when to schedule the appointments, to which judge, and to which starting time slot. And it has to fulfill the certain norms. So you can see the norms on the left, and on the right you can see a schedule which we aim to make. And you see above the schedule of judges, below the legal assistants, and the colors are certain cases, certain appointments. So you have 3 appointments per case. And the hearing has to take place on the same time for the judge as well as for the legal assistant. So then we have made a mixed interlinear program that starts on the left, but it has a total of 41 constraints, so it did not fit on the slide. And on the right, you see 2 of the basic planning constraints. So you have only 1 appointment per time slot, and no double appointments can take place for a certain judge or a certain legal assistant. And then I have used the data set in order to test the mixed interlinear program. So I used a data set created based on the inflow of cases in 2019. So I had the number of FTE of judges and legal assistants. I have the lower and upper limit of the cases in a month, and I have a distribution of the appointment durations. And we have used this data set in order to test the mixed interlinear program, by which we obtain such a model, and we can conclude that the problem can be solved within reasonable time. But we had to expand it to a Markov decision program, as not all appointments are known in advance. So in the Markov decision program, cases arrive according to a stochastic process, which fits the reality. And we also have the addition of the uncertainty of appointments arriving in the future. And we also start with a field agenda. So we start with something as on the left, and we have to schedule a new incoming appointment. And we have to schedule a case one by one instead of scheduling a bulk in once. And also we have an infinite horizon instead of a finite horizon. So we now start with the figure on the left, so an already filled agenda. And we have to schedule a new incoming appointment, or new incoming case, which has 3 appointments. And you can see it on the right. So the blue case has arrived, and it has to be scheduled at 1 judge and 1 legal assistant. So the Markov decision program, it contains of a certain state. So a state is where you start with, the filled agenda, and the incoming appointments. And you have to make the decision when to start the appointment for the certain judge and for the certain legal assistant. And the transition probabilities we've used in this Markov decision program are based on Poisson arrivals and a uniform distribution of appointment durations. But a Markov decision program is really large and hard to solve. So therefore we use the Approximate Dynamic Programming algorithm in order to solve the problem. And we've used the post-decision states which is an iterative algorithm in order to solve large Markov decision programs. But that brings a challenge as it deals with a value function approximation. So you have to make an approximation of how good or how bad a solution is. And we've made that using basis functions, and we've set these basis functions based on literature and expert opinion, and also some trial and error. So in these basis functions, we've made a couple of assumptions. So the preparation lasts 4 to 6 time slots, the hearing 1 to 2 time slots, and the writing of the verdict 6 to 8 time slots. So we have made around 10 basis functions, but we will now show some of them. So the first is the number of free time slots of length 1, 2, and 3. In those free time slots, you can only schedule a hearing, so you want to have not as many of them. Another basis function is the first moment 6 consecutive time slots are available, since that is the moment a preparation can take place. And as the preparation has to take place before the hearing and the writing of the verdict, we want to have this first moment as soon as possible. Another basis function is the first time slot the judge and the legal assistant are available, since both have to be available at the same time for the hearing. So you want to have that moment also as soon as possible in order to fulfill the set norms. So the convergence of the Approximate Dynamic Programming algorithm, we've used a toy-sized problem in order to test this convergence. And this toy-sized problem contains 2 judges and 2 legal assistants, and a time horizon of 5 days, so 1 working week. And the time horizon can move up to 7 days using a rolling horizon. And you can see here the objective function on the left for 50 iteration, on the right for 500 iterations. And you see that the objective function really moves, but kind of stabilized around 250 iterations. So that would be enough to solve this toy-sized problem. And that took around 48 minutes. So that was only a toy-sized problem. One needs to make this problem formulation also work for larger instances. And also, we did not take along that during the process, cases can be scheduled or have to be rescheduled. And one also has to collect more data, since we now had to make a couple of assumptions. And when more data has to be collected, the basis functions can be reconsidered in order to fit better to reality. And besides that, the differences and similarities between jurisdictions and locations can be investigated, such that this model can also work in the other jurisdiction and for the other locations. So to conclude with, we have made a planning strategy in order to plan certain cases within Judiciary. We started with a mixed interlinear program, if all appointments are known. And then we expanded this to a Markov decision program in order to incorporate the uncertainty in the arrival of the cases as well as the duration of the cases. And this problem was solvable in reasonable time, and it performed better compared to myopic policy. But there has to be more research in order to be able to solve larger problems, such that the model can work in practice. But I'm happy to say that the Rechtspraak will fund 2 PhD students to continue on this research, such that such a mathematical model can be used in the future in order to schedule the cases in the Rechtspraak. So that was my presentations. Are there any questions?